welcome to today's lecture. Today we are going to see a very important topic of image processing and computer vision. It is edge detection. This is the agenda for today's lecture. First we will see why do we need to study or why do we need to compute edges in the images. Then we'll define what is an edge, and we will see that edges will be actually computed with the help of image gradient. So we'll see what we mean by image gradient, and then we will see some standard edge detection operators like Prewitt operator, Sobel operator, Robert Cross operator, Laplacian operator, and log operator. When we are computing the gradient, we'll see that we can compute the gradient. Gradient will be basically the first order derivative. And mostly we will be using the first order derivative to compute the edges in the image. But sometimes we'll also use second order derivative. Using the second order derivative also we can compute the edges. So the operators that you see here, these three operators are actually based on first order derivative, and the last two operators that we have here, they are based on second order derivative. So let us first see some motivation. So if I just show you this picture, and if I ask you what is this object, I think most of you can tell what this object exactly represents, right? So it's very easy to guess that this is representing an aeroplane. Similarly, if I show you this image, by looking at this image, very easily you can say that this image is, of what animal, right? Similarly, if I show you this image, very easily you can say that this is a kind of flower image, right? So when I am showing these images, which are actually having some pixels as on and rest of the pixels as off, or in other way you can say some pixels are 1 and rest of the pixels are 0. When I am showing these images, and later we'll see that these images are nothing but the edge images. When I am showing you these images, you can very well find out what are the objects these images actually represent. So from these examples, we see that lot of information we can extract from the images where we have pixels represented in the form of, where you have some pixels which are white and rest of the pixels are 0, or in other way, more precisely, we should say that we can represent or we can obtain a lot of information from the images which are the edge images, just edge images. So if entire image is shown to us, obviously we will get a lot of information. But if in place of showing the entire image or this complete image, if we just get the edge image, we see that a lot of information even can be extracted from the edge image. Okay. So a common question may arise in your mind that why do we, when we get more information from the complete image, why should we go for the edge image? Okay. So there are certain advantages that we get when we are processing our images with the help of, or when we are implementing our applications with the help of edge images. One direct advantage you can see that if you have represented your image as edge image, to store this image, you don't need actually the grayscale, gray values, right? This can be represented in terms of binary image, right? Where you have black pixels represented at 0 and the white pixels represented at 1. You don't need 8 bits to represent these pixels. You just need only 1 bit to represent. When you are setting that bit as 0, it represents black. When you are setting that bit as 1, it represents white. So one advantage directly that you can see from here is that to store these images you need less amount of space. Okay. And similarly, another advantage that you can see from here is that when you are processing this image, you have to process each and every pixel. But when you are processing these images, if you have, let's say, stored your image in such a way that you can directly go through your edge pixels, then you don't need to actually go through all the pixels to process this image. You have to just go to the pixels which are the edge pixels, and just by doing some processing at those pixels, you can do the processing on the image, right? So you don't need to explore each and every pixel here in the image. We can just focus on the edge pixels. And if you compare the number of pixels in the image and the number of edge pixels in the image, you will find that the edge pixels are very, very less as compared to the total number of pixels that you have in your image, right? So the second advantage you can say that if you are processing edge images, it needs less computation because the number of edge pixels are very less as compared to the entire pixels that you have in your image. Okay. There are a few more advantages that we'll see later. So, for example, here these edges are. We'll find that these edges are up to some extent invariant to illumination or contrast issues, and up to some extent noise. For example, if you, let's say, take this picture, the example of this picture, and you change the illumination, you will still find that, or you change the contrast of this image, you will still find that you will be able to locate these edge pixels, right? So these edge pixels are invariant to a lot of image issues like illumination, contrast, and so on. Okay, so these are some advantages when we advantages we get when we process edge images. So that is why we are interested in actually studying the edge detection. Okay, so now let us formally define what we exactly mean by an edge. So in all these examples that we have seen here, in all these examples, whatever these highlighted pixels that you see, all these pixels actually collectively define the edges. Okay. Now, what are these pixels? How are we locating them in any given image? So we will find that all these pixels, wherever we have, like all these pixels where we have put the intensity as 1 or intensity as white, all these pixels are actually some way differentiating two homogeneous regions. So if you see across these pixels, on one side, like for example, we are saying that this particular this white line is representing the edge for this image. So if you just superimpose this line on this image, you will find that that line will be somewhere like it will be lying somewhere here like this, right? So if you on this line, if you see one side of the line, you will find that you have one type of pixels. If you see the other side of the line, you find that you have another type of pixels. So you can see that these edge pixels are these pixels which we have highlighted here on the second image. They are nothing but a kind of boundary between two homogeneous regions. On one side, you have one type of region, and on other side, we have another type of region. And we are saying that these two regions are homogeneous because all the pixels that you see here in this side, all are having similar nature. Similarly, if you see all the pixels that you have on the other side, they also have the similar nature. Okay, so that is why we can say that the edge is a kind of boundary between two homogeneous regions. Okay, and as I just explained, these homogeneous regions will be distinct to each other. If you compare one region with another region, they will be distinct. But if you compare the pixels within the region, you will find that they will be uniform. The nature of the pixels within a region will be homogeneous, right? So whatever intensity you are seeing for, let's say, this pixel, almost similar intensity you will see for the another pixel within the same region. So in summary, we can say that edge detection is nothing but finding out all these pixels in the image which actually separate one homogeneous region to the another homogeneous region. Okay. So our goal in edge detection is to consider 2D image, which will be 2D array of pixels, and then find out all these curves or line segments or contours. I mean, you can call them by any name. The idea is to find out all these curves, line segments, or contours in the image, which basically separate two homogeneous regions. Okay. Now, when you are computing these lines or curves or segments, you are not going to get one particular line in one go or a contour in one go. all these contour or line or curves, they are going to be actually collection of pixels. So to detect a line, if let's say line contains 100 pixels, then all those 100 pixels need to be detected. Similarly, if let's say a contour contains 50 pixels, 50 pixels which are separating the one region from the another region, so then all those 50 pixels need to be detected. So once we detect all such pixels and then combine them, then you will find that they will become a curve or line or a segment contour. Okay. So when we detect these edge pixels, actually, if you analyze the nature of the intensity that you have at a particular edge pixel, you will find that on one side you have a one type of intensity and on another side you have a different type of intensity. For example, let us say you want to find out this particular edge pixel here. Okay, so let us just consider the profile, intensity profile in this direction. So if you see the intensity profile in this direction and just consider what kind of intensity you see at this particular pixel, you will find that on one side, on this side, you will have lesser intensity because on this side the pixels are little dark, and on this side your pixels are little white. I mean, if you notice previously, let me just show you here. So if you just notice this region, on one side you have dark pixels, and on the others, other side at this particular pixel here, you have white pixels. Okay, so and similar to, so what we actually see here, that on one side you have different kind of intensity, on another side you have different kind of intensity, and this you will find if you consider all the edges that are all the edge pixels that we have highlighted here. If you consider all these pixels here, if you superimpose all these pixels on the first image, you will find that all the highlighted pixels that you have here in the first image at that particular pixel, whether you consider a horizontal profile or you consider a vertical profile, at that particular pixel you will find that the change in intensity happens with respect to pixel gray value. Okay. You can just take other example. For example, on this leg part here, you are saying that let's say this particular pixel is a edge pixel. Why we are saying that this is an edge pixel? Because when you consider a profile like this, with respect to this point, on this side you have pixels which are white, but in the leg region the pixels are a little dark. Okay, so in other way we can say that these edge pixels are the point where there is you find a kind of intensity change. On one side you have a different kind of intensity, or on other side you have a different kind of intensity. So we can say that to detect all these pixels in the image, what we have to do, we have to consider our image, and at each and every pixel we have to find out what kind of intensity change the pixel has. If you see any intensity change a particular pixel when you are moving from, let's say, left to right or from top to bottom in that particular pixel, if you find any intensity change, then you can say that that pixel is an edge pixel. If you don't find any intensity change, then you can say that that pixel is a non-edge pixel. For example, if you consider, let's say, that particular pixel here, and now you consider intensity profile, let's say in this direction, then you'll find that let's say this pixel is here. So you'll find that with respect to this pixel, on this side also you have similar kind of pixels, and on this side also you have similar kind of pixels. So that is why there is no intensity change there. So you see here there is no edge in this particular region. But if you consider those pixels which are actually falling on the boundary of, let's say, on the horse on the pixels which are defining the boundary of this horse and the background, at those pixels you will find that there will be intensity change. And that intensity change will be sometimes in x direction, sometimes in horizontal direction, sometimes in vertical direction, and sometimes you will find that this change may be in both the directions. Okay, so ultimate idea of finding out the edges in the image or edge pixels in the image is actually turns out to be computing the intensity difference in the image for pixels and then analyzing them to compute the edges. So how will you find out that intensity difference? So to compute that intensity difference, we'll see that we will be using gradient. We'll define gradient in the next slide. This, in simple terms, gradient defines actually the first order derivative in x and y direction if you are talking about a 2D function. Okay. So to compute the edges in the image, we will compute the gradient of each and every pixel in the image, and then we will do some kind of post processing to finally get the edge pixels. Ideally, when you are talking about a intensity change, let us consider this example. So in this example, what we see when we are moving from this direction to this direction at this particular pixel, you find a change, right? If you map this red line that I have drawn, and if you just just get the intensities which are below this red line and plot them as 1D curve, you will find a curve like this, where on this region you have intensity 0. On the other region, you have intensity 1, and there is a pixel here where the change is happening, where this is going from black to white. Okay, this kind of edge is called an ideal edge. Ideal step edge. What you see here, practically, we may not find this kind of sharp change in the derivative or sharp transition with respect to the intensities. This change may be like this, as you see here, where you have two regions where when you are moving from one direction to other direction, at the boundary or at the line which is partitioning these two regions, at those boundary points, the intensity may not change suddenly, it may change gradually. Like for example, if you see any black and white image, maybe exactly this image, but for example, let's say you have a black and white board and you have clicked its picture. So even though this region is completely black and this region is completely white, but if you take its picture, you'll find that at the edge, at these pixels which are defining the boundary, the change in the intensity will gradually happen. So like for example, this is a black region. So when you are moving from black region to white region, at this point here, slowly you'll find that the intensities will go to white. Okay, so practically we'll find that our edges will not exist like this unless the edge has been created in the image has been created in computer. If practically we have acquired that image through our camera, we will find that even though the regions are completely black and white as you see here, but practically the change in the intensity will look something like this, where when you are moving from one region to another region, the intensities are gradually going from black to white. Okay, so to compute the edges, we have to compute the intensity change, and this intensity change we are going to compute in terms of derivative. And here derivative will have two parts, because since we are going to compute derivative in both the directions, in x direction and in y direction, because in image the intensity change can happen in either direction. When you are moving in x direction, you may find a particular pixel intensity change, or even at that particular pixel you may be moving from bottom to top. Then also you may find the intensity change, and sometimes that intensity change may be in a generic direction, right? So to compute the complete information of the edge, we actually need to compute two values. One, the derivative, which will actually tell the intensity change at a particular pixel, and then also these edge pixels will have a direction. So compute the direction. We'll see that we'll consider the derivative in x direction and the derivative in y direction at a particular pixel, and then using them we'll compute the direction of the edge. So we are going to get from the direct derivative we are going to get the intensity change, and that will define the magnitude of the edge. So more the derivative or more the change, you will find that the magnitude of the edge will be more, which will actually tell that the edge is strong. And if this magnitude or this derivative is less, that will tell that the edge is not very strong. And as you can see, this derivative is telling you the change. So if the derivative is high, that means that change is high. So and if the change is high, that means there is a very clear-cut intensity transition in your image, so that will define a strong edge pixel. And if the transition or the intensity change is not that high, then that will define a weak edge pixel, or I mean a kind of poor edge pixel. And with the help of the derivative that we, as I just said, whatever derivative we are getting in x and y direction will compute the direction of the edge. Okay. So now let us see. So when you are computing the derivative in x direction and derivative in y direction with respect to the given image, and if you collectively put that together, this actually defines the gradient. As I earlier said, gradient is nothing but the derivative in x direction and derivative in y direction. We are just saying x and y direction because our images are 2D images and we have just do two directions. But if you are talking about a three-dimensional function, then gradient will be the derivative in all the possible directions. So x direction, y direction, and z direction. For us, the images are only two-dimensional kind of functions. So we are talking about gradient in only x and y direction. And this gradient in x and y direction can collectively define gradient at a particular pixel. And if you calculate this gradient for all the possible pixels in your image, you can say that and at a particular pixel, whatever you are computing, we'll see that it has it can be defined from that we can compute two type of quantities. One is the gradient direction. By considering this del f by del x and del f by del y, we can compute the direction of the gradient, which is nothing but the tan inverse of del f by del y divided by del f of del x. Okay, and from this gradient we can also compute the magnitude of this gradient, and this magnitude of the gradient will define the edge strength. More the gradient, more the edge strength, or we can other way you can say strong the edge. If the gradient is less, the edge is actually weak edge. These are few examples where we see gradient in different directions. So if you consider the first example, in this example, the intensity change is happening only when we are moving in x direction. There is no change in the intensity if you are moving in y direction. You take any column here in this image, you will find that across that column all the pixels have the same intensity. So that is why when you are computing the gradient of this image, we find that gradient is in x direction is this, but in gradient in y direction is 0 because there is no change in y direction. Okay. Similarly, if you see here, in this particular image, gradient exists in y direction, but there is no gradient in x direction. In this image, the change is happening when you are moving from in horizontal direction, and also the change is happening in the vertical direction. So since the change is happening in both the directions, so to find out the resultant change, we have to consider both the gradients. And if you compute the theta, which will tell you the direction, with the help of theta, you can find out what will be the resultant gradient direction. Okay. And always we'll find that let us say we have an edge here like this. So its gradient will be, the direction of the gradient will be always perpendicular to the direction of the edge. So as you see here, the edge is in this direction, so its gradient is actually in this direction. And this is happening because at this particular pixel, if you consider your change in x direction will be in this direction, change in y will be in this direction. So if you compute the resultant, you will find this direction, which will be perpendicular to the direction of the edge. So please remember, the direction of any edge is actually perpendicular to the direction of the gradient. Now the question comes how to compute gradient or how to compute the derivative. We can interchangeably use the word derivative and gradient. In case of gradient, you can note down here that we are talking about the partial derivative. Okay, so whenever we are saying here derivative, we actually mean partial derivative. So now question comes how to compute the derivative. So in continuous domain, if you have a function fx and you have to compute derivative at a particular point x, let's say, how do you compute it? This is a standard formula we use, and we compute the derivative, which says that derivative at a function f at x is equal to fx plus dx minus fx divided by dx. So you have x here, fx plus x plus dx here, and the difference between these two, which is dx. So by just using this standard formula, you can compute the derivative at a particular point. And if you go to your school mathematics, you'll find that all the derivative functions, all the derivative formulas have been defined by using this standard formula. Okay. So now here, when you are computing the difference in images, sometimes just to have, so according to this formula, this says that if you have an image pixel, let's say like this here, and you want to compute the derivative here, you subtract the value of this this intensity to this intensity. That means you are subtracting this to this to get the derivative, right? You can say that in your image, this is x plus dx. So what will be fx, the intensity at this pixel? What is dx, the intensity at this pixel? And you are just subtracting that and dividing it by the difference. So difference is anyway going to be 1, because if you compute the difference of the coordinates here, you will find the difference will be 1. If this is, let's say, if this has coordinate 2, 2, then next will be 3, 2, and so on. So the difference is this dx is going to be always 1 in our case. So there's one way of computing the difference at this particular pixel. Now in image processing, sometimes to make it more symmetric, in place of to detect the edge at this particular pixel, in place of subtracting this intensity to this intensity to this intensity, we'll subtract the intensity of this pixel to this pixel. Okay, just to have a symmetric computation. So if you are using this kind of approach, then in that case you can say that you are subtracting the value of fx minus dx to fx plus dx. And in this case, what will be the difference between these two? It is going to be 2 dx, because the difference between first pixel and second pixel is dx, and similarly the difference between this pixel and this pixel is dx, so the total is going to be dx. So we can use this formula, first formula, or you can approximate and use this formula. We'll see that there are some operators which are based on this formula, first formula, and there are some operators which are based on the second formula. Sometimes we'll also see that in place of using the first derivative to find out the edge pixels, we will also use second derivative. So second derivative, as we are defining the first derivative, if we just again take the derivative of this, we get the second derivative, which is which comes out to be this. You can analyze this formula later, and if you have forgotten, you can just go through your school mathematics where you studied differentiation and integration. You will find these things. Okay, so as I was saying that there are some formula or standard edge detection operators which are based on first derivative, which is defined like this. There are some which are based on this, and you can say if you are talking about a second derivative, then some of them will be based on second order derivative. So here we are seeing two examples. One is this, which is based on the first order derivative, and another example here, which is based on the second order derivative. And one more thing, let me just tell you. So all these formula that I have defined here, they are defining the derivative in x direction. But and we have considered in this example the function which is just 1D function. But in the later slides we are going to extend it for the 2D, because our images are 2D, and to define the gradient we need partial derivative in x direction and partial derivative in y direction. So I think it's very easy to extend or get those formula from here, because as we are defining the gradient in x direction, if you change the variable to y, you will find the formula for the y direction. Okay. So here we are defining, if you see, we are defining these edge operators by using this differentiation and differentiation formula that we see here. And here we are defining these operators for both the directions. This is the operator which is obtained by considering the gradient in x direction, and this is the formula which is obtained by considering the gradient in y direction. And this formula, as you see, this particular formula has been derived by using this kind of definition, the first definition, right, which is saying that just consider the first pixel, and in that subtract the second pixel. Okay. In our simple, in terms of our simple image mathematics, we can say that when we are computing the gradient, as we are saying that we need to, in this particular case, we need to subtract the intensity of this pixel to this pixel. We can, we can say that we are actually filtering this image at this particular pixel by filter -1 and 1. Because what we do in filtering, we multiply this value of the filter to the corresponding pixel, this value of the filter to that corresponding pixel, and then sum that. And exactly the same thing we need here. When we are computing the gradient at this particular pixel, we want to subtract this intensity to this intensity. So we can say that this computation of gradient or the change in intensity is nothing but filtering of the image with the help of this operator or this filter, we can say. So this filter is defined, since this is defined in x direction, whatever intensity changes we get out of this filter, they will be in x direction. If you apply this filter, which is -1, 1 transpose, which you can say that it is something like this. You have 1 here and -1 here. So when you are applying this filter, let's say particularly at this particular pixel, then you will be subtracting, let me just draw it again here. So again, let's say you are applying the same kind of computation in the y direction. So in that case, you will be actually subtracting this intensity of this middle pixel, this pixel, to this pixel. Right? So this is nothing but saying that you are filtering, you are performing filtering operation at that particular pixel by this filter. Okay, and how we are obtaining these filters is easy to see. From they have been directly obtained from the definition that you have here for the derivative. Okay. The second example that you see here, or the second operator that you see here, they are actually based on second order derivative. And why we have 1 here, -2 here, and 1 here. If you go to the definition of the second order derivative, you can see when you are computing these additions, the first term has 1 coefficient, second term has -2 coefficient, and third term has again plus 1 coefficient. So to represent this in terms of matrix, or in terms of vector, or in terms of this filter, we can say that the first term is 1, second term is -2, and the last term is 1 here. Similarly, if in the vertical direction, again you will have a filter -1 to 1 transpose, which is nothing but 1, -2, and plus 1. Okay. All right. So when you are doing, so one thing we have understood from all this discussion is that when you are computing the edges, we have to compute the derivative. We have to compute the derivative of the image pixels. Now, once you get the derivative of all the pixels, or in more precisely, we can say that we are computing the gradient, which basically says that you are computing the derivative in both the direction, x direction and in y direction. So to compute the h pixels in any given image, you have to take the image and you have to compute the gradient at each and every pixel. But now if the gradient is available at each and every pixel, how will you find out that a particular pixel is an h pixel or it is a non-h pixel? So you will find that if you have any, if you consider the 1D profile at particular pixel, which is an h pixel, you will find an intensity change like this. On one side you will have a one kind of intensity, on another side you will have another kind of intensity. Now if you compute the derivative, when you consider that you have a derivative, just to compute whether this particular pixel is an h pixel or not, you are computing a derivative. So when you compute derivative, you will find that with respect to this pixel, you will get a highest change. But if you move in this particular pixel in this direction, that change will gradually decrease. If you go on this direction, again the change will gradually decrease. Let me just give you an ideal example. Suppose you have an ideal edge, which is like this, where on one side you have, let's say, 0, or maybe let's say intensity 10, and another side you have intensity, let's say 50. Now if you are computing the derivative, you will find that, and let's say computing an image or the function corresponding to this one here. So in this case, you will find that when you are computing the derivative, you will find when you are computing the derivative on this direction, you will have all 0, 0, 0. As soon as you come here, suddenly you will get a very high value, and then again as you move this direction here, again your values will become 0. So in ideal case, if you are computing the derivative, if it is an ideal edge, you'll find that this this derivative image will be having just one peak at a particular at edge pixel, and all rest of the places this will be 0. But as I just said, that in ideal, I mean in practical cases, you will find that even though you have a sharp change in your image, but when you are considering the intensity profile, this intensity profile around the edge, it will change gradually. So that is why when you are computing the derivative at this pixel, you will have a high value. But if you deviate from, if you move to this direction or in this direction with respect to this pixel, whatever intensity difference you are getting, that will not go suddenly 0, it will gradually go to 0. So that is what you say. So with respect to this pixel, which is an edge pixel, you have very high derivative, but as you go in this direction, the derivative is slowly becoming 0, and after some time it becomes 0. Okay. So to detect the edges in your given image, you can say that once you have computed the derivative or you have got the gradient, you have to actually look for those pixels where this derivative value or the value of the gradient is high. Because in this example, you see that wherever there is an edge pixel, the gradient has peak. Okay. So given an image, if you have to compute the edge pixels, you just compute its gradient image, and in that gradient image you go to each and every pixel and then find out if that particular gradient is high gradient or it's a low gradient. If it is a high gradient, you can say that that pixel is an edge pixel. If it is not a very high gradient, you can say that that pixel is a non-edge pixel. And this high and low, we'll see that we'll define based on a threshold. If the value is more than a certain threshold, we'll see that it's a high value, or otherwise it's a low value. Okay. So with respect to the first derivative, as I just explained in the previous slide, at edge point in your gradient image or in your derivative image, at the point where you have edge pixel, your gradient will be high, because if you compute the first derivative of this profile, this function, you will get a function like this. But if you compute the second derivative, derivative will look actually like this. So as I just said, that to find out the edge pixels, you can look for the high values in the first derivative, but corresponding to that high value, you see that in your second derivative, that value becomes 0. So other way you can say that in place of computing the first derivative, you compute the second derivative and then look for the points or look for the pixel in your derivative image where intensity is 0. Because corresponding to this peak, if you go to the second derivative, that particular pixel will have the 0 intensity change. Okay. Or in the language of edge detection, we say that is the 0 crossing. That point, because the point where you have 0 value in the second derivative, this is called 0 crossing, and the reason is that on one side you have, if you consider this second derivative profile, on one side you have one type of, or you can say the positive values of your function takes positive values, on the other side function takes negative value, and where does it cross, or where does it go from positive to negative? At this particular pixel. So this is called the crossing, and the value is 0 here, so it's called 0 crossing. So I'm just again repeating the same thing. To detect the edges, you have to compute the gradient. If you are computing the first derivative, you can look for the high values in the first derivative image. But if you are going for the second derivative to compute the edge pixels, then you have to look for the pixels where you have 0 value, because those 0 value will correspond to 0 crossing. These are some standard operators that we normally use for edge detection. The first operator that we are going to discuss here is the Prewitt operator, and in all these operators, please remember that they are in some way they are going to give you the gradient. And as I just said, that gradient is going to be computed in x and y directions both. So these operators will, in all these operators, you have to define the two matrices. One to compute the value in x direction, another to compute the value of the gradient in y direction. Okay. So in Prewitt operator, your operator is defined like this, which if you analyze, this is actually if you just analyze this particular row, this particular row actually tells you that you have computed your derivative by using the formula that we defined here, this way, right? What this formula says, that if you are computing your derivative at x, you are not considering fx. In the previous case, you are considering fx, but in the second case, you are not considering fx. You are subtracting fx minus dx to fx plus dx. That means you are giving zero importance to the central pixel. So if you just analyze the matrix corresponding to this, you can say that if you are computing the edge at this pixel, you are giving zero importance. You are giving importance to this pixel, here you are giving importance to this pixel, and actually you are subtracting the value of this pixel, intensity of this pixel to this pixel. So in terms of this operator or a filter, you can say that you can define a filter like this, where when you are filtering your image with this filter, the pixel corresponding to this will be multiplied by -1, the pixel corresponding to this will be multiplied by +1, and when you are adding them, this will be nothing but subtraction of the intensity of fx plus dx to fx minus dx. Okay. So in case of Prewitt operator, in case of Prewitt operator here, we are exactly using that formula. But now you might be thinking that why this and this row is there. So to take the decision, Prewitt suggested that you should not only compute the gradient at that particular row corresponding to a pixel. Suppose you are detecting edges, let's say you are trying to find out that whether this pixel is an edge or not. So normally with by using that formula, we should subtract the value of this to this. But Prewitt suggested that in place of considering only these differences, you also consider differences from here and consider differences from here, and then take the decision collectively. And the reason here is that if, let's say, this pixel is, if you remember in the previous classes we discussed that if our if a particular pixel, if you analyze the intensity of that particular pixel, its nature is bit similar to what you have in the surrounding pixels. So sometimes because of the noise, a particular pixel gets changed. But since we are thinking that, we are assuming that the nature of a pixel is same in a small neighborhood. So if, let's say, this pixel becomes noisy, we can still think that this particular pixel or this particular pixel will not be that noisy. So if we to decide whether this particular pixel is an edge pixel or not, in place of taking decision based on only these differences, if we include this difference and this difference also, it will be the result that we are going to get will be more reliable. So that's what Prewitt suggested, that in place of computing the difference only in that particular row where the edge lies, or in that particular column where the edge lies, you take a little neighborhood and compute the difference on the pixel which is at up and down. And similarly, with respect to this gradient, you compute the difference on the if you want to detect this pixel as whether this is an edge pixel or not, you compute the gradient on the pixel which is on the left, and also the gradient on the pixel which is on the right, and then collectively take the decision. Okay, I'm just going to finish this in a few minutes. So if you have gx and gy, then to compute the gradient, you can use this formula, and which will tell you the value of the magnitude of the edge. And if you want to direction of the gradient, you can use this formula. And typically, as if you, this also we have discussed that this is computationally more costly. So by subtracting their magnitude also, sorry, by adding the magnitude of x and y also, you can get the gradient. In the case of Sobel operator, this operator is very much similar to what we have in Prewitt operator, but in this case we are giving more importance to the row or the column where our pixel lies, and lesser importance to the neighboring pixels from the rows or columns. Okay, that is the only difference. And once gx and gy is there, you can define the gradient and the direction of the gradient, magnitude of the gradient and the direction of the gradient. Okay, this is the last slide, and after this I'll just stop. In the Robert Cross operator, in place of computing the gradient in x and y direction, or in the horizontal and vertical direction, Robert actually suggested to compute the gradient in the diagonal direction. So suppose if you have an image like this here, and you want to compute whether this pixel is an edge pixel or not, till now you have computed its difference between with the pixels which are on the neighboring pixels with this on horizontal direction or in the vertical direction. But now in the Robert Cross operator, Robert suggested to compute the intensity difference in diagonal direction. So here basically you are going to compute the difference of this and this pixel, and similarly the difference of this pixel and this pixel, and then based on that you are going to take the decision, right? So if you are you can see these two operators gx and gy. These will define actually the gradient in corresponding to these two directions, and once you have these two values, as usual you can just compute the gradient of magnitude of the gradient or the direction of the gradient to find out the complete information about the edge. Okay, so let us stop at this point.